My name is Richard Berkowitz, and you're welcome to the course in quantum mechanics. Now, the course is given in English. I know that some of you, I guess, don't feel so comfortable to express themselves in the language. So first of all, don't be ashamed. It's an opportunity to exercise your English. And if not, you could ask in Hebrew and I'll translate and we'll try to get through it. Okay, so basically we start this course late and we won't cover all the whole of the material in quantum mechanics. I posted on the Moodle or the Lambda, whatever it's called nowadays, the syllabus. We will follow it more or less. So basically, I don't want to start with negativity, but nevertheless, we won't get to the point of the hydrogen atom, nor will we get to to studying angular momentum. I'm still hopeful that we will get some result, but anyway, we will start and go and try to make it as a good experience as we can expect under these conditions. Okay, I see that we have here almost a full house. So it's very nice. And your mates are coming in next week? Yeah.
Yeah, they're arriving here this Friday.
They're arriving on Friday, so it was already announced that there will be a rerun of this lecture on Monday for those of you that couldn't take part in the course. So let them know. Try to look at the recording of this lecture. It will save all of us some time. Okay, so what is quantum mechanics? Well, I'm trying in this course something new. I'm putting each week a clip. I saw that they already posted two of the clips, which gives a bit of a wider angle, a more philosophical overview of what we are doing in quantum mechanics. During the lectures, I'll concentrate much more on the technical, mathematical parts of quantum mechanics, because in the end of the day, that is what you will need. But I don't want you to come out with the feeling that that's all that there is to do in quantum mechanics. Quantum mechanics has real challenges in understanding what we are doing there, why are we doing it, what does it tell us about reality, about nature, and a lot of these questions are open. On the other hand, from the point of view of actually getting out predictions, results out of the theory, quantum mechanics, to my taste, and hopefully after the course you will feel the same, is actually easier than classical mechanics. Why? Because at the end of the day, quantum mechanics is an algorithm. You take some assumptions, whether you understand them or agree with them or feel comfortable with them, that's a completely different question. But once you accept it, assume like you're living in a computer game, these are the rules, that's what we have to do. Once you accept these ideas and concentrate on how to perform the calculations, it's much more straightforward than classical mechanics. Okay, let's start by comparing what do we do and what don't we do in quantum mechanics compared to classical mechanics. Okay, so in classical mechanics, the typical critical thing we want to know is we have a particle and someone has to tell us at what point is it and with what momentum does it move. So someone comes and tells us we have initial conditions and we come and it's at some time and one asks the question at time t what will be x and p? Where will it be and with what momentum? In order to answer it, someone has to tell us what are the forces that operate on the particle, or if you're a bit more sophisticated, what is the potential? And once you have that, you write down your equations of motion. Could be complicated mathematically, but at the end of the day, you can say where you'll find it at time t and with what momentum. And basically, it could be at any given t. Okay. And that you spent courses in actually already in high school. You did it in the first year, then you learned a more sophisticated mathematical mechanism to calculate things in analytic mechanics, and that's it. Okay, quantum mechanics is different in some sense. Because at the end of the day, it's a theory of probability, not of, it can't answer specific questions, it can give you probability. And one thing I would like you to get used to from the beginning is all physical information on the particle lives in the wave function. I'm using the word wave function, although I haven't yet defined it for the simple reason you have heard this in modern physics. You know that something like this exists. Perhaps you don't know how to do calculations with it or all kinds of calculations with it, but you know that this entity exists. So what replaces these initial conditions in quantum mechanics? So this is the classical. We have a function. It doesn't have to be a function. It could be a vector. Actually, we use a function if it's a continuous system. We use a vector if it's a discrete system. We will see examples of discrete systems somewhere in the course. And this thing holds all information that we need or can know about the system. Everything is in this wave function. And what we are doing throughout the whole course, actually also in the second course, quantum mechanics 2, is to know how to take the wave function from an initial condition to something at a future time, how does it develop, and how do I extract physical quantities out of it. There's nothing else. Okay, so in the first lecture we'll try to tease out all kinds of properties out of a general wave function. And we will go on to do something about a very short refresher due to the situation about linear algebra, which is very important in quantum mechanics. And then we'll treat all kinds of systems. Particle in a box, a particle in harmonic potential, and so on and so forth. Unfortunately, we won't get into a particle in electromagnetic potential or in Coulomb potential. What is it physically? Actually, before that, someone notes something strange about this function. No momentum. What's your name? Yeah. Very good. Here I needed two variables to define it. And here I write a wave function which depends on x. And all of you who did modern physics knows you take this wave function and do things with it. But what happened to the momentum? The point, and one of the most important points, and we'll spend some time in understanding it, is that in quantum mechanics, if you know x, you don't know p, and vice versa. So, and now I'll tell you something new. The same ways that I did quantum mechanics, writing down the wave function of psi of x and t, I could have written it and could go through the whole algorithm of seeing what will happen at time t and get an answer and extract everything that I have here. I could have extracted it from here. And we'll spend some time in how do I translate between this language and this language. And I'll tell you another secret. There's an infinite ways to write the wave function. It's just my choice. Okay, so we have a wave function, and some of you have heard already that the wave function is connected to probability. Okay, what do you remember about?
The square of it, I think, is the probability. Integral, and you square it and you do it equals to 1. And from minus infinite to infinite. And
okay, you did. You started okay and jumped.
I jumped to something else. Okay.
No, it's not something else, but one has to stop and, what's your name? Leo. So you have to stop. You did 5 steps instead of 1. So basically, one of the interesting quantities that I can be interested in is the probability. And what is this probability?
Density or probability?
No, exactly. I have to be a bit more careful. X, and if I want to be even more pedantic, I'm not necessarily working in one dimension. I could be in 2, 3 D dimensions, so I'll put here a vector to remind me that it could be a vector quantity, and that's the probability. Why do I need the thing? Because this is the density times a unit of volume, then I get probability. Actually, I could have ask what is the probability to find the system at a given momentum. Same answer. Yeah.
Can you explain what it means e to the power of 3?
Yeah. And excuse me, I'm incapable of drawing higher dimensions. Working on it.
If I walk in the
So-
x and y, it will be the x dy.
You understand why I don't like to draw. So d to the power of 3 of x
The x dy.
dy dz or dx1, dx2, dx3, or whatever is your preferred mathematical symbols for that. There are many of them. So the only thing I say is this is a probability. I have to find it somewhere in space. I have to say my space is one-dimensional, two-dimensional, three-dimensional. During the course, we'll spend a lot of time in one dimension. Not so much because our world is one-dimensional, although one can create experimental situations where it's effectively one dimension, but it's just easier mathematically. But so you are used to see here dx, but it's not necessarily dx. Okay. Now, if I have another physical quantity I'm interested in, find a way to write the wave function as function of that quantity, square the wave function, you have the probability to find this quantity. As I said, moving from this quantity to this quantity to some other, it's a mathematical procedure, well defined, and all we have to do is follow it. Yes?
Usually in classical mechanics we use our observables are based on position and momentum. But in quantum mechanics we can have both. So how do we arrange to do that?
Okay, so basically what this tells you is that when the wave function has all information, I'll take an analogy to a simpler quantity. I have a vector. So I have here some vector now I'm using a different notation. Okay? Now, come to me and say, well, I have a point at x1, x2, x3. And I say, okay, I know where it is, because I know now, and then I stop a moment and say, actually, I don't know on what you're talking. What am I missing?
The coordinates.
I need a basis. x1, x2, x3 compared to what? Now, it's the same business here. I can give you the information as function of x. That's for a certain basis. I can give you as function of p. That's a different basis, but it's all a shift in your base. Now I'm a bit too general, but we will define these things exactly. That's within the algorithm of the quantum mechanics. The only thing I can't do, I can't specify the probability of x and p because they don't exist. Can't give you the probability of x, can't give you the probability of p, I can't give you both. That's Heisenberg's uncertainty. Didn't define it yet, you don't understand exactly what I'm talking about, but it's all there. Sometimes there are physical quantities that can coexist. Let's say position and spin, magnetic momentum. I can't tell you that the electron is here and its spin is this way or that way. That one I can. Depends on the system, we'll see how it depends and why. All of that is the algorithm. Okay, lovely. Now I get to your point. Yeah. If this is a probability, there are conditions on probability, and the most trivial conditions that I have on probability, someone can tell me?
Sum of
It's
all
normalized.
of all the cases are equal to 1.
Exactly. I can't have a probability that doesn't sum up to 1. Don't quote me. We'll see within 2 or 3 lectures that we are loose with this definition, and I'll explain why, but to be completely consistent, yes, it has to sum up to 1. And moreover, it can't be negative. It's not enough that I can't sum up to 1, I can't have negative probability, it's meaningless. So that's the reason for the square. The wave function can be negative, can be a complex number, everything's good. No problem at all. Not only no problem, it sometimes has to be. You can't solve the problem unless it's complex or negative or whatever. But once I'm trying to extract something out of the game, meaning probability, then I have to square it and square it in a way that I get a positive number. And if it's complex, I multiply it by its complex conjugate. And it all has to sum up to 1. So P or if I write it differently instead of okay. So we call it a wave function. Sometimes we call it also a probability amplitude. Why? Because if we square it, we get the probability. Okay. One thing that I didn't speak about was in classical and quantum mechanics. Usually, we are not only interested in what is the initial condition and what is the final condition. We want to know what happens on the way. So, in classical physics, give me the initial condition. Use the equation of motion, and I'm able not only to tell you what is initial and final points, I can tell you the trajectory. Quantum mechanics is very similar and very different. What do I mean by very similar?
You can also get the equation of the wave function.
I can give you an initial wave function.
But you can't really tell the place of
I would like to be a bit more careful. What's your name? Ben? To be a bit more careful, I can tell you the wave function at any given time once I know the potential of the system. How do I do it? Your good old French Schrödinger equation. So I can give you the wave function at each given time. I can give you even more. I can plot the probability at any given time. Of course, once I have a wave function, can I answer you where the particle was at any given time? Answer is no. Not only it's no because I have not too good physical theory. It's not because my measurement is not good enough. It's for the simple reason that I have no way to speak about the properties on the way. I have only a way to speak about the probability. Now you can stare at me and say, this is nonsense. I'm sitting here. I know that I'm sitting here. And who stops me to answer the question, where am I? And the answer is, actually, as I emphasize in my clip, it's quantum mechanics actually has two steps. We will concentrate a lot on the step from how do I get my wave function from here to there. We will spend a lot of time on answering the question, how do I calculate out of the wave function all kinds of physical properties? But the skeleton in the cupboard of quantum mechanics is how do I know actually where is the particle? And the answer is clear. I perform a measurement. What is a measurement? I have a couple of clips about what is a measurement. But for us, in an algorithmic way, you started with some wave function, you come after time t, you perform a measurement of its position. I'm telling you it's here at x1. I measured it, it's there. Okay. How do I continue the development in time of the system?
Schrodinger equation.
With the Schrodinger equation, but not with this wave function. Why? Because this wave function
Is for this initial. This is another initial.
tells me there is a probability for finding it here, 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 and here. And you measured. No, it's here. Probability of being anywhere else is 0. So you can't ignore your measurement. You measured, you know. So you have to start with a new wave function that tells you that the particle at time t of the measurement was here. A delta function if you want. And then continue with your Schrodinger equation, and you'll see what happens further on. But pay attention that if I didn't perform a measurement on the wave, I will have a different wave function because I changed here the conditions in the middle. Yes.
When you are telling me the measurement of the particle, you create a new wave function because I have a new initial rule.
Okay, so it's one of the sexiest questions in quantum mechanics. Huge argument. Now, the world is complicated. There's all kinds of interpretations on what happened at this point. The traditional, and I would say for students who start studying this problem of quantum mechanics, it's the easiest to understand, although it's counterintuitive. On that, one of the famous things that Feynman said, shut up and calculate. Don't ask me questions, and that tells me, okay, you measured, your wave function collapsed. What do I mean? I had a wave function with some amplitude everywhere, or close to everywhere. And then I performed a measurement and it's here and nowhere else. That's a collapse. And it happens, that's your new wave function. You want to continue to know what happens to the system. Shut up and calculate. Continue from here and go on. Another interpretation that is nowadays very popular in Hollywood, which is the many-world interpretation, which I don't have yet the full language to explain, but I'll give you a taste of it, tells me, well, you measured, but you are also a quantum mechanical entity. You have also a wave function that describes your probability. What happened here? It's correlation between your two probabilities. The electron you measured is now here, and my position is I saw the electron here. And for the versions of me that didn't see this electron here, there's another branch of the wave function which continues under that I observed it here, and other branches where I didn't measure at all, and so on and so forth. That's the many-world interpretation, which tells you that every measurement is not a collapse but branching. Now, does it matter for our algorithm? No, because you continue to calculate in your branch. I don't know about you, but I never woke up and said myself, now I feel that I'm in this branch and that branch, and so on, but that's my feeling. Perhaps someone here feels something else. So, is there a difference between that language and just saying the wave function collapsed? The answer, as far as we know today, no. And since we have no difference, we can put an experiment and find out which one of those interpretations is correct. So if you're a hard-nosed realist, you say, shut up and calculate. Leave me alone. There's nothing that I can't pull out of that information, therefore it's not relevant. Other people will argue, no, we have to understand what really happens here, but there is a difference between stating that we have to understand to be able to understand. And we didn't bridge it, and some people will claim there's no way to bridge it, and other people say there must be a bridge, but here we are. Okay, so we have the wave function. Now the additional ingredient that we have conditions on the wave function that it has to be normalizable, meaning that square the wave function, integrate over the whole space and get one. And you have to tell me how does it progress in time, how it does it develop in time. That's the Schrödinger equation. And okay, it's a differential equation that tells me.
You put it harder, then you change it from up.
From next to
Okay, so let me be consistent.
V is a function of time also?
Could be.
Because modern we learn only
And until the second half of your second semester, well, in the next lecture we will actually discuss why we like so much stationary potentials. It has a good reason. It makes life much easier, but in our world, actually the most common field or force is electromagnetic, and you know that it depends on time. So if I'm writing a general Schrödinger equation, I have to take into account that the potential can depend on time. Guys, Well, if you have a question, ask. If you want to do something else, do it politely. Okay, so know what's happening, what potential does exist in your space, know an initial condition, know to solve a differential equation. You're good. Give me psi x at time t0. I'll tell you what it is at time t, and if I'm unable, so my computer can tell you. It's a simple first order differential equation. At this point, some of you should get really angry with me.
Why the first order? You have
Right, Ben? This is nonsense. Can't be. Why? Because all of you have learned special relativity, or I hope that all of you have learned. All of you know that time and space are on the same footing. Why are you coming here and giving me an equation that has t derivative to first order and space to second order? Cannot be. It's nonsense. You present it in an exam, the lecturer should throw the answer to the bin. It's meaningless. So, and Schrödinger wasn't an idiot. And when he started to think about how to describe the development of the wave function, he actually first suggested an equation with a second derivative of time. And this equation actually gave him a lot of nonsense. For example, all energy states can exist till minus infinity energy. What does that mean? The electron can go down and down and down and down in all energy levels and give up photons, and you have perpetuum mobile, an infinite source of energy, because you can always continue to go down. So what can you do? You can either give up, say, I have no idea, nature makes no sense. And then another way is to say, look, I'll put relativity on the side. Why? Because I don't know how to treat it. But if I do that, I can write down an equation, and why a first order? Because as we'll see, it's very important that you have a ground state, and first order promises that you have a ground state. And some younger person will come up with some solution to what you do about the fact that it doesn't fit relativity. So and so, most problems are for particles at low velocity, and therefore relativity shouldn't change much. Okay, and actually it didn't take long, 2 or 3 years. Dirac came with a solution. That's the Dirac equation. And now you can stop me and say, excuse me, why do you waste our time on studying an equation that is wrong? Teach us Dirac equation. Don't mess with us, give us a wrong equation. And there are two answers to that. The first is, let's take it from the point of view of utility. What can I do with it? Schrödinger equation describes a lot of systems in physics, gives you very good results for them. It is much easier mathematically, so why not use it? That's one answer. Second, to study the basic ideas of quantum mechanics, it doesn't really matter. The basic ideas are here. How the wave function progresses with time. We have quantum mechanics, we have field quantum mechanics, we have string theories, who knows what else? All of them keeps this basic idea that we have a wave function. Mathematics grows more and more and more complicated. The general structure, no. So it's a very good system to understand fully the basic concepts, and you'll do Dirac equation in the graduate studies, you'll do quantum field theory in graduate students. As graduate students, well, at the moment, no one still does string theory as graduate students in this university because we don't have particle physics, and second, until now, not much useful has come out of it. I hope not to. No string theorist on the internet sees it and will get some angry email about it. But it's a very good system into which to start to learn quantum mechanics. Now, mathematical simplicity is a very important. I'll just give you a small taste why Dirac equation is more complicated. One of the things, you can't write a scalar wave function. It's a vector with 4 components.
In both sides of the page.
You can't have a vector of 2 components on one and 4 on the other. It doesn't work. You have scalar here, scalar there. Why 4 components? Someone could guess.
The complex number.
There are complex numbers also.
I wanted to say 4 dimensions, but I think you said it already.
No, although 4 and 4 sounds connected,
They
no.
use quaternions or something like that.
People try to write quantum mechanics of quaternions. There's no successful theory till now, and people have been at it for half a century, so whoever thinks is a bit confused what are quaternions, it's not important for this course. You have real numbers, you have complex numbers, you have 2 additional ways of grouping numbers. Why only 2 additional and not infinite? I can't explain, perhaps some mathematician can explain that to you. But anyway, it's not important. We stop at complex numbers. Why 4? Because of
the relativity.
no.
Space and
No, but it's not the 4. What are the 4 different components telling us? It's the probability to be in spin up or spin down. That's 2 of them.
And antimatter.
And matter and antimatter. And that was the greatness of Dirac's equation. Spin they knew exist, and we'll see that we'll put in at different occasions spin by hand into the wave function. but matter and antimatter was something no one thought about. It was just forced because of the mathematics. You want to write down a consistent relativistic formula, you have to have 4 components. Now, what they are, then it was understood that it's matter and antimatter. Okay, but I think it's the last time we'll say something in this course about matter, antimatter, or Dirac equation. Now, another, well, in the syllabus there was promised also a historical background, so I'll say just a few. Actually, Schrödinger equations wasn't the first equation to describe the development in time. Someone knows what it? Yeah, it's Heisenberg matrix mechanics. And it appeared a few months earlier. Most physicists couldn't make heads or tails out of it, for the simple reason that no one studied linear algebra as a physicist, because it was an irrelevant field. On the other hand, differential equations, any physicist worth his salt knows to solve differential equations. So this description became the easiest entry point, although we will use matrix representation quite a lot for certain problems, especially problems that have a finite number of possible measurements, and I already mentioned one, spin. It's the easiest, only 2, up or down. And again, this guy, Dirac, came and proved that they are both the same formulation. Any differential operator can be written as an infinite matrix. So if it's infinite, it's not very useful for a continuum, but if it's finite, it becomes useful. Let's say, for example, if you want to solve things, quantum mechanics on the computer, a lot of time, computers are discrete, a lot of times it's easier to write it as matrices. Okay, so if it's a wave function in a differential equation, it has all the mathematical conditions that we want. We want it to have a derivative, a second derivative, being continuous, all the usual mathematical niceties that you want out of a wave function. We will see that in all kinds of cases we'll circumvent it. We will not be too strict in applying this condition. Okay. So, knowing this and knowing the fact that it's a probability, we can actually show that Schrödinger equation is forced by the condition that if we have a probability at some region and time passes, the probability has to go somewhere else. It can't disappear. Now, if some of you are alert, they should again stop me and say, nonsense. We have heard in modern physics that a photon can be created or be absorbed, right? So it disappears. But photons cannot be described by Schrödinger equation for that reason exactly. We can put it in the potential. We can't describe it in Schrödinger equation. What we have to do then is to go to quantum field theory in order to describe a particle that can exist or stop to exist. But Schrödinger equation describes only particles that are here, don't disappear, are not created because the probability has. So an electron at room temperature is a good example. Very high energies, it's not a good example because there is enough energy for pair creation. An electron positron pair can be created at high energies. Again, that's quantum field theory, that's not the Schrödinger equation. Okay, so how do we show this? Let's say I have some region of space. And I have some density within this region of space. What is this density? In principle, it could be anything. Particles, material, who knows? Here it will be the probability of being in this region. So what do we know? Well, first of all, dx is another way to write d to the dx. Since this is equal to 1 by definition, and the derivative of a constant is 0, this is simply 0. All it tells us, particles are not created, nor are they destroyed. They're always there. Just a different way to say the same thing.
You are not writing the limits, they are
Over the whole space. At a given space, which will be this, no, of course. And that's exactly the next statement. And this is delta V. We define some portion of space. So, if I have some density here, probability or material density or whatnot, the only way it can leave this area is to flow through the boundary. Right? If it flows out, it decreases. If it flows in, it increases. But that's the only way to change the density within this region.
Understand why this is what I get? But this is the flow.
This is the flow out of it. I'm leaning on the fact that you actually have seen it in, somewhere in classical mechanics. It's not completely new.
This is how in magnetic and electricity.
It appears within thermodynamics, electromagnetism. Everything I'm doing in the next few steps, you have seen it within Gauss theory. It's the same because it's the same concept. The only thing I've changed is calling it psi square instead of rho or something like that.
It's minus because it gets out of this.
Right. If it's going out, so it decreases inside. If it's going in, it increases.
Because of the normal vector, right?
It's the normal on the surface. Actually, I'm not very particular here because it's the last time you'll see it. I'll rewrite it using the Gauss theorem. So that's Gauss.
What is that way over there?
This one?
Yeah.
It's the velocity coming out.
Oh.
And don't worry, as I said, this is the last time you see it because the whole point is to show you that Schrödinger equation comes out of conservation of probability. Then you put it in a drawer and forget about it. Basically. So, remember, this is rho. I simply call rho times V the current density. What is current? Density times velocity. Like in an electrical conductor. Okay. So, go and rewrite it on the top. Another few steps and we'll go out for a break. So let me just rewrite it to the top. One thing that I know about J, at the infinity it's equal 0. Because I can't leave the space. Why do I need it? I'll see it. We'll see in a moment. We said it.
You made just the opposite of Gauss?
I made the opposite. I went to infinity, integrated over the whole surface, but at the infinities J is equal 0. I know that 0, so I know what I knew when, as I began. Until now, we didn't do anything that's quantum mechanics. Now, next step is to use the fact that the density of probability in quantum mechanics, and now we're connecting it to quantum mechanics, is the wave function times its complex conjugate. Okay, I think it's a good point to take a break. We'll take a quarter of an hour break and reconvene here around 3:25. Can you stop the recording? Someone please remind me on technical things, books, homework and stuff, just to say a few words. Okay?
אמרת שאנחנו עושים את זה איכותי, 4 דברים, אתה יודע כמו נגיד
לא, יש לך, טוב שזה לא מוחלט, אני לא רוצה לדבר את המוח לעוד אנשים, יש לך פה, יש פה פח. זה למה אני לא במכבי תל אביב. וקטור 4 של 4 פונקציות גל שבעיקרון יכולות להיות שונות אחד מהשני. זה עוד סיבה למה אנחנו לא מתחילים עם מכניקה קוונטית עם חיה כזאת, וכמובן אז האופרטורים חייבים להיות טנזורים.
רגע, למה 4? אבל יש אחד בכיוון הזמן כאילו?
לא, כולם פונקציות של x ו-t, זה לא.
אוקיי.
אז אם אתה עושה את זה בבסיס הנכון, אז שתי אלו הם ספין אפ בשני
אוקיי,
אלו הם
בסדר.
ספין דאון, ואחד מהם זה, נגמרו לי האינדקסים, נקרא לו פרטיקל, נגטיב, פוזיטרון.
לא בדיוק הבנתי מה קורה פה.
לא התכוונתי.
לא התכוון שתבין, רק הראה לך כאילו מפרצות.
זה למה לא מתחילים עם זה. אין קורס שמחליק.
זה קוונטים 2?
לא, זה קוונטים מתקדם.
זה תואר שני כאילו?
המשוואה האמצעית היא, אני לא חושב שהיא נכונה באופן כללי, אני מתכוון שבמקרה הפרטי שבו זרם הסתברות לא יוצא למערכת, אז כל מה שכתוב...
כן, אמרתי, at infinity, אני חי באינסוף.
אז מה זה אומגה?
אומגה זה כל הרחב.
כתבתי לה, היא אמרה לי, סליחה, היא סימן קריאה, סליחה, אני מבקש לדבר עם המרצים. נתתי לה ככה, אחי.
לא רוצה שמישהו יראה את ההקלטה ויכתוב
זהו, כתבתי לה, תראה מה כעסתי, הולך לקראת הודעה, שלא...
מה רשע? לא שלחת לי. זה
שלחתי לך פעמיים.
מה?
אתה צריך לעשות בעצם נגזרת ווקאלית של מה הסיכוי לעזור. תחשוב על זה במקום הסתברות החלקיקית. זרם של אלקטרונים.
זרם של זורם.
אז אתה, צפיפות המצבים כפול המהירות של הזרימה.
כן, אני מבין למה המשוואה הנכונה במובנים של... זה כמו מכניקה זורמית.
עד פה זה מכניקה קלאסית, אין שום
בזמן.
אבל המהירות הזאת זה כאילו... איך אני ממש את המשוואה?
אני מקבל פה רכיב עם הזמן.
אז בשביל זה אתה צריך לדעת איך משתנה הצפיפות קרוב לסרטון.
כשאתה אומר נגזרת ווקאלית, אתה מתכוון...
לא אחי,
הרי לא חייב להיות שהזרם בכל מקום עוזר.
למה רשמת לבד?
אז אתה מתכוון לקחת נגזרת חלקית יותר זמן על השפה?
על השפה עם כיוון.
כפול הגורמה וזה יהיה
היא אמרה לי, סליחה, עם זמן קריאה, אני מדבר עם המרצים. כתבתי לה, אין לי לדבר.
לא הבנתי, אבל רשמת שאתה לא בא, אז מה היא מתווכחת? זה לא
לא יודע
חובה.
אחי, כתבתי לה מעבדות, זה כן, כתבתי לה מעבדות.
זה כן חובה?
כן.
לא בא, מה?
כתבתי לה מעבדות.
אבל נגיד יש לך קורס עכשיו שהשר לא מעביר, אני חלקיקים אלמנטריים, זה שילוב של קוונטיקה ויחסים. שם יש לך נישור או איפה?
אני נכנסתי כמישהו אחר.
משוואת דירה משתמשים בה בעצם בתחום של פיזיקה אטומית. למה?
זה גם קוונטי, כי זה קטן וזה גם מהיר.
זה קוונטי ומהיר ולא נעלמים לך במצבים
כמו
חדשים חלקיקים. אבל בכל חלקיקים מה אתה עושה? עושה התנגשויות של חלקיקים במהירות מאוד גבוהה, באנרגיה מאוד גבוהה, ויוצא מזה, לא דווקא,
יש הרבה דברים שקורים.
אומגה פלוס פלוס, כל הגן חיות של חלקיקים של שנות ה-60 וה-70 ניסו להבין את זה. עכשיו בשביל דבר, ברגע שאתה אומר את הדבר שחלקיקים, מספר חלקיקים לא נשמע. הדבר הזה זה לא.
אז זה לא קשור בכלל.
אתה לא יכול לתאר את
כן,
זה.
זה יכול...
אתה לא יכול. אז מה קורה שם? על רגל אחת. שוב, אני לא מצפה שתבין את כל העניין. פה אתה בעצם קוונטת חלקית. שם אתה לא מקוונטט חלקיק. אתה מקוונטט לא שדה. בוא נעצור רגע ונחשוב. בשביל לתאר אלקטרון בפיזיקה קלאסית, היה לך חלקיק שיושב ב-X ואת זה אתה צריך. מה זה פוטון? מה זה המקביל לפוטון בפיזיקה קלאסית?
פעם זה משהו חסר מסה, כאילו.
כן, חסר מסה, שמהירות האור.
לא, אבל איזה גודל פיזיקלי אתה מדבר? שדה חשמלי. אתה צריך לקוונטט שדה, חיה אחרת. אז אתה צריך להתחיל אותם רעיונות, יש לך, אם אתה רוצה להתחכם, אתה שואל, אתה יכול לשאול מישהו מה היא משוואת שרדינגר של פוטון, התשובה תהיה למה? בשביל העוצמה, שזה הסיכוי של לראות שדה חשמלי מסוים, זה אי בריבוע.
נכון.
פגשת
מה טהרה כאילו.
העצמה.
וזה מתקשר לגוף שחור גם.
נכון, אותו דבר.
אוקיי.
אבל,
הכל ככה.
אבל, למה לא עושים את זה? כי
אני
במשוואת מקסוול H בא נופל אך ורק מהסיבה שלו מקרה
עוד השנה הזאת.
עבור פוטונים האנרגיה היא
אבל-
H בר כפול אומגה.
אם זה משהו
אז
יצור
זה
אחר,
משני
אז זה פחות חמור.
הצדדים אתה מצמצם את ה-H ורואה את משוואת
כן,
מקסוול.
אני חושב, יש מספיק פעם אחת כזה.
אז-
זה די מיינד בלואו.
אה,
אנחנו נלמד את זה, לא השנה אבל.
בתורת שדות, תואר שני. זאת אומרת, יש פה המון, אתה לומד שפה חדשה לגמרי, אם אתה בסוף
תשלומים?
תצא מפה ותגיד, מכניקה קוונטית? זה פשוט להגדיר פונקציות על הילברט
ואם הם לא נותנים
ולעשות
לי?
להם טרנספורמציה. בינתיים זה סין. לא.
לא, בסדר, אז אני יורד המסתירות.
אז לעבור משפה לשפה, היו כמה חכמולוגים שאמרו, חבר'ה, בוא נזרוק את המכניקה הקלאסית, אבל מתחיל לתואר ראשון כזה לומד כלל. איכשהו פדגוגית זה לא עובד, אנשים רוצים בריאים.
רוצים לרדת איתי שנייה למסתירות? שכר לימוד.
שכר לימוד, אתה מבין עכשיו?
לא, אחי, צריך להיות אישורים.
זה נכון. לא טעית.
אין לך... גדול. מה מאשר מחווה לדורון? קיבלתי משהו בבית ואין לי כבר, אני לא אמשיך לתת את התשובה עכשיו.
תכתוב לו, זה נכון, ולכן צדקתי. ולכן 100. תודה.
אתה לא מספר קצת מה עשו פה?
כי הוא רק אותי זה מצחיק על לא לכתוב לו רבים שבגורים פה לא לכתוב.
כאילו בגלל האוניברסיטה שבצד, כאילו זה מסתיר.
אבל זה לא מסתיר.
בדיוק, זה שאני אומר. לא. מישהו יושב שם.
זה ככה אתה צוחק על אנשים תמימים ויושבים שם, אתה לעשות את זה.
מה? לא, אני צוחק עליה.
אני צוחק עליך כשתעשות את זה. כן, רואים שאתה אחי. אתה קורא את זה?
כן. מה?
מה הוא כתב שאני רוצה לכתוב?
סביר לי לזכור כל פעם אחת. יש את הדמית נסה. חשבנו על זה איקס. איקס, מה זה איקס?
מי שב-X אני מישהו בתרגיל שלי, אני גם טעיתי המון בהסכם השימושים וטעיתי וזה. אבל כשתסתכל על התרגיל שלי לא רואים את זה. אני נראה כאילו, אני גאון למרות שאני לא. אתה מבין את הגאוניות שלי? אתה נראה כאילו אתה מין... למרות שאתה גם טעית, אבל פשוט עשית מחיקה ולא רואים את זה. כל מיני כאלה. זה משדרים את העמדה שלך.
שמע, מה יהיה כוח לדורון? אין סיכוי הוא טוב בכלל בשיעור בבית וכזה קרסטרים ועושים.
צריך לא לדורון, תעשה לי טוב.
יש פה דבר. התחלתי מדרך טיפה שונה ואז כאילו.
סתם חד אז תכתוב בו עכשיו אירוע.
זה לילדים.
יפה, אז רגע, פה קודם מידע בדיק. לא, אני נדמיין את הבדיק. זה עוד סרט של רפלייס, מה שזה ביטוי שלהם.
וואי. כפול. אחד
וואי, ועוד אחד כפול, זה לא יתפסק. זה להקליט.
כן. לכן, מה טוב מזהות ידועה.
טריוויאלי. ברור לכל אידיוט שסיים.
XY שווה את הפתרון. זה השני, רגע, זה לא, לא.
תכתוב, הושאר כהוכחה על העבודה.
רגע, סיל...
סליחה, הושאר כתרגיל עבודה.
מה? זה לא אותו דבר. אנחנו צריכים להראות שזה זה וזה לא מה שנכון.
צריך לכתוב את מה שנכון.
בסדר, אבל עושה את זה באלגנטיות, נכון? אני עכשיו לא שמת לב. אז זה לא יודע. נכתוב את הדבר, כן.
די, אבל.
לא מכיר את הזהות הידועה.
איזה ליצן זה? אוקיי.
בדיוק זה, זוכר אותו, זה אפשרי. X. מה זה Y? לא.
ינון,
כן,
איזה מחזור, כאילו איזה מסור בשנה שלנו היה הכי גדול? כאילו פיזיקה מתמטיקה או נצטרך משמע אפילו? מי
מה שמעת הכי גדול?
אחת כמות אנשים.
פיזיקה מתמטיקה ממש לא.
לא?
משהו. ממש קצת.
מה? לא ממש.
אנחנו 10.
מה אתה מוריד? אנחנו זה 20, רק בקבוצה אנחנו איזה 25 ואיזה 5 שם.
יש שם. בוא נעבור על האנשים ששם.
תקשיב, מה, אתה סתם מוריד?
זה ממש. אנחנו 10.
אני אמרתי לו 20, אני רציתי להתגאות.
אני דולף דור, הוא כימיה.
שנייה. קודם כל,
אנחנו 17 בקבוצה. אני דולף דורל. נימי לא. סבבה.
כל אלה שאספו.
לא, נימי בלי קשר, היה אחד חוגי.
בסדר.
לספור גם את היאללה.
היה להם תרפיות, איפה היה?
4.
אוקיי, טוב. אז
5.
אנחנו לא הרבה.
6.
אני סתם חייתי בשלב.
7. וואו.
מה?
שבע?
אנחנו רק 7?
7?
7 בקבוצה לפחות.
זה חצי מכמות האנשים שהיו במחזור שלו.
הייתם איזה 15? 14?
13. שזה טוב.
מה? אנחנו...
תעגל כלפי מעלה.
מה, אתה שמעת עליהם?
לא. אני שירתי בצבא אחרי שהייתי תיכוניסט, אבל לא סיימתי אז, עכשיו אני כמעט אף אחד לא עושה את זה, אז אני כן היה לי הליך.
אשכרה, מה עשית בצבא?
כאילו אנחנו לא פה.
הייתי מה שנקרא, השם של אבי זה טכנאי קונסולת, הייתי בגדוד 9272, שזה נכון בזה? כן. מתעסקים עם סיבים אופטיים. זה הדבר הכי דומה שאני יכול לחשוב על זה. כאילו, זה לא אותו דבר, אבל נגיד, הסוג של הרכיבים והסוג של העבודה, איכשהו לא.
היה טוב?
אבי בסן.
כי זה גם, אני לא הולך לאקדמיזציה, זה היה תפקיד סדיר כזה, בוא נגיד ככה, סביר פלוס, הוא לא היה רע, אבל הוא גם לא היה ממש לא רע. הבאסה הגדולה זה שהעבודה של הקונקשן היא יותר במשמרות בצורת העבודה. אז היה סבבה. עכשיו אני פה, זה כל זה המקום האהוב עליי בעולם.
כן.
Okay, so missing a few people, but everything's return. Okay, so something I forgot to mention at the beginning. General things. Books. What book do we need for this course? The answer is basically I don't follow a particular textbook, but in quantum mechanics there's a whole lot of good introductory textbooks from Merzbacher, Park, Sakurai, Koentanuji, an endless variety of books. Anything that says quantum mechanics or introduction to quantum mechanics more or less covers the material. Some of them are more mathematical, some of them are more general, but all of them are good. I will put a list on the Moodle, but frankly, it doesn't matter. Any textbook covers the material. Koentanuji, for example, and it's this huge book, actually two volumes that are, it's good for exercise, even just lifting them gives you some good cardiovascular exercise, but it's very detailed, very precise, for some people too detailed, too precise, but anything that you find suitable, check the library, or if you happen to have it, everything is okay. Now, about homework. 30% of your grade is homework. Why? Because it forces you to go and really do something with what we present in class. Submit it in time, because the reason to do homework is that you come to the next class more prepared. So you don't have to all the time sit there and wonder, what is he talking about? Did we do it in the previous lecture? That's the reason, and it also is an insurance policy. Sometimes when it gets to the exam and something doesn't come up, and it gets a less than ideal grade, and why not buy this insurance policy? Okay, I think I covered everything. Any other? I understand that there is maybe one student here in Miluim. If you know his name or he wants to contact me, let me know, and we'll try to work out something.
No quiz.
Excuse me?
No quiz.
No?
Quiz.
No quiz. Just simply we're down to 10 lectures, putting in also a quiz in the middle. We'll
How much much is the homework, the percent of the final grade?
30.
Ah.
See the recording I talked about
okay,
it
sorry.
2 minutes ago. Any other questions?
What is your email?
Yes. ریچرد.برکوبیץ @BIU. Berkowitz, BERKOVITS.
He's also in the model, yes.
It's in the Moodle.
Okay,
It's
so-
secretaries have the web page of the.
Okay.
I would be rude and tell you if you can't figure that one out, you're in the wrong course. Okay, so we got here. I'll go and stick this definition into the derivative of rho. Okay. Can't argue with that.
What happened to the integral?
What happened to what?
The integral?
I'm just now treating, if you remember this.
Oh, yeah.
Derivative of a multiplication of two functions. I can think about psi and conjecture as two independent functions. Question?
Yes, I know maybe I go a step forward, but we know that we can split this to time and space, and we see that the time is cancelled, so why we don't go to the space?
So the answer is you're wrong.
Okay.
You can't split it. You can't split it in one condition that will prove the next lecture, which is in the case that the potential is constant in time. If not, this you can't do it. So since I didn't say anything about the potential at this point, no, I don't want to split because
We don't.
it's not general. Okay, so we have these quantities. We know something about it. What do we know? That the Schrödinger equation tells us something about it. That's a Schrödinger equation. I'm not bothering writing the x's and t's. Okay?
Where is the 2m and h bar goes to?
You see, in Unix it's a little bit not good. It's a minus. And a square hill, of course. Okay, I can take this equation and complex conjugate it.
also the psi's are
Yeah.
Right. And here.
Why is it V?
And well, for simplicity, we'll forget about this.
Well, we have the complex number.
No, V is a potential. It should, although I wrote complex because sometimes one is not very careful, and if it's an electromagnetic potential, one writes e to the power I. But the truth is, you have to take them the real part. So I will.
The start of the equation.
What did I miss here?
Why there is
there
a
isn't a
minus?
minus.
Why there's a minus?
There is no minus.
There is no minus.
no, yes, because it's conjugate. You
Conjugated.
Ah,
Conjugated is a very simple procedure, algorithmic. Any letter, put a star above it. Any I, put minus I.
נכון. סוציומטרי.
You,
Yeah, all good.
so just be a
I
compiler.
didn't notice the eye.
It's important because
Yeah.
this kind of, especially in quantum mechanics, will conjecture a lot.
Okay.
And if you screw up changing the sign of I,
Yeah.
it could give you stupid results. The good thing is that you'll immediately recognize it as stupid because, for example, you'll get a probability that's complex.
Okay.
So you know you did something wrong, and usually it's something like that. Okay. Can multiply this equation by psi conjugate and multiply this equation by psi. Oh, excuse me, just. I cannot put it before operator. Let me subtract this equation from this equation. Just subtracted it. This falls off because psi conjugate times psi is equal to psi times psi. Let's take a look what's written here. Okay, because if I perform derivation of psi square, I get psi exactly what's written.
Why'd you put it in absolute value?
Hmm?
Why'd you put it in absolute value?
Because I'm too lazy to write psi conjunction. And I'm being a bit lazy. Yeah, just divided by IH bar.
Are you missing the star on the rightmost comment?
Of course. And plus, I think it's. Oh, no, if Okay, so I'm going back and looking at the equation I started with. What is the conclusion I can derive?
That J is not.
And J is exactly
Riç'רד, not it equals to the gradient.
Now, let me do another step here. Okay, sorry, I missed here a step. I should have done also. Okay, and
Shouldn't there be a star above the...
and I should return the minus. Not here.
Still missing the star. The minus inside the.
No, here comes a minus from here. Here it's a plus.
I mean inside the brackets. Or the equation.
Here, of course.
And also star.
Hmm?
Star also on the right.
Okay. That's why you come to lectures, to exercise. Follow up. Okay. So, we have two benefits of this whole exercise. One is to see that the way Schrödinger thought about how to obtain this equation, meaning he looked on it as an equation of conservation of probabilities, and you see that his equation actually follows it. And another thing that comes out, it's the first time you see that we pull out a quantity out of the wave function, which is not just squaring it. This is the current, and in a moment we'll understand, not in a moment, in one or two lectures, we understand that this is not a physical measurable quantity, but it's still a conceptual quantity. The probability current at a point. Who asked me how it's calculated? Someone during the break. You asked me how it's calculated.
The velocity.
The velocity J is
The current.
the current. So you see how it's calculated.
Oh yeah.
Just get it. Okay. And this is the segue actually to the second most important ingredient in quantum mechanics. We know that we have wave functions. How do we calculate physical quantities? And as you see from the current, basically a physical quantity is coming and performing some kind of operation on the wave function. So it's not a big surprise that we need operators in order to extract a physical quantity out of the wave function. Okay. I'll provide a small dictionary of operators. I won't prove at the moment that these are actually those that are connected to the physical quantities, although with time we'll see the reasons for it. So operators are usually, we put a hat symbol above them so we'll know it's an operator. And this is the operator of energy. We've seen it somewhere. Schrödinger equation.
usually find the energy greater as h.
No. Yes and no. If I want to express it as Hamiltonian, yes, but I don't. Remember, okay, I'll jump a moment and return to it. What is a Schrödinger equation?
Energy.
It's the
That's a Schrödinger
that's weird.
equation. Nothing. Oh, you're again 5 steps ahead. We don't know what are eigenvalues and and this is not an eigenvalue equation yet. This is just a Schrödinger equation. In a moment I'll define the Hamiltonian, okay?
But you're choosing a basis, right?
right.
From that you get a Schrödinger equation. So, no, the energy is not the comparing the energy operator operated on a wave function is equal to the Hamiltonian operated on the wave function. That's the Schrödinger equation.
Is that little x in the potential subscript also not that one? The left one. Is that also an operator or
No. That's the operator at position x. Operator operates at a position. In a moment it will become clearer. Okay? Lovely. So what do I do with this operator? Does that give me the measurement of energy? No, it cannot. I'm putting in a wave function, I'm pulling out a wave function. I don't know what to do with it. And physical quantity that can be measured has to be a real number. The most important thing about passing a test in quantum mechanics, you calculate some physical quantity, it's not a real number, you did something wrong. Now, if you did a complicated calculation and got a wrong number, you lose a few points. You did a calculation of energy and answered 2I, you lose the whole question. Because one of them is you're not such a good mathematician. The second tells me that you didn't understand anything of the course. So, I don't mind someone ending up a calculation with 2I, writing down, look, I did some mistake. I don't know, I don't have time to find out. I did my best and couldn't find out. I know it's wrong. That's half a problem. Somebody quietly writing down the energy is too high and happy with the result, that's a big problem. So one good thing about quantum mechanics is it has a built-in error correction code. Usually if you do a random mistake, you'll get something with a complex number, so you know something is wrong. So, what can we calculate with operators? Now we know everything about quantum mechanics. We have a wave function that I told you contains all physical information. I have an operator which tells me how to calculate out of it a physical quantity. The only problem I have, okay, I get this Lego block, I get that Lego block, how to connect them together. Okay, first thing that we can calculate is averages. Now, the word averages is the exact description. Most textbooks, especially the older ones, has the using observational value. This is a bad description on all levels. Because as I said, if I measure an average position at 0, doesn't mean that I observe it at 0. It only means that if I'll do out of the same initial condition the measurement again and again and again and again, and average over all these observations, I get what they call as observational value. But no, therefore, I don't like it. I want to use averages.
In the sense of expected value?
That's sometimes used as expectation values. Also, it's used a lot of times. It's a very bad description because, as you know in life, an average is not what you always expect out of a measurement. Yes?
Is this also what's called observables, or that's something else?
No, observables is the general name to things that can be measured in reality. Every observable has an operator with which I can pull out things that are connected to this. Okay, so how do I calculate averages?
The wave function, the operator, the samud, I don't remember how to say.
Conjugate.
The conjugate to the wave function and the integral.
Exactly. So, I'll write the average of operator O, which could be any one of these operators. To form an integral. While you're treating probabilities, you're calculating the average, you average over the whole space. No matter what O is, first glimpse on the algorithmic nature of doing calculation in quantum mechanics. What does it mean? Let's take an average of x. Let's assume that I'm interested only in the x part. So if it can have y, z, I don't care about it. Because this is a simple multiplication, I can move it out. And now I write it down explicitly. Okay? Could leave it in between, doesn't really matter. Should have written T. Actually, because I have no dependence out of P on Y and Z, and I know that the complete integration on P will give me 1. Okay, so to calculate the average x, I look at the probability to find it at x. What about the probability of finding it at y and z? It's not interesting for the calculation of the average x. And go and do the integral. Yeah.
But P is also a function of y and z, maybe.
Yeah, but once I finish to integrate over y and z, I'm assured that this integration will give me 1.
I don't understand why.
Probability.
Probability in this integration is 1, yes.
It's not quantum mechanics, it's just probability. Right? I want to do what I want to know what's the probability of finding at x while I don't care about y and z. Y and z have to be constructed in such a way that it will give me 1. Otherwise, it's not a legal probability. Right? Okay. what will happen if instead of just a moment, I want first to do something simpler. Some function of R. I want to calculate R squared. I want to calculate R to the third plus R. Why? I don't know. Z. And this isn't relevant. Okay? So I have r to the square, x squared plus y squared plus z squared. That's the result. Again, algorithm. Just stick it in, do the calculation. Okay, a bit more interesting.
This is assuming that it's not a complex
Excuse
number.
me?
You're assuming it's not a complex number.
No, I don't assume. It has to come out from the calculation as not.
No, I mean when you move it out of the.
F of R is not a complex number, right? To calculate the average momentum in its direction. Perform a derivative of x of the wave function, multiply it by its complex conjugate, integrate, multiplied by minus IH, you'll get the average momentum.
It's not have to be zero.
A very good question, and now I'm expecting a good answer.
Because the integration give me a real number, and we say that the average have to be a real number, and I have imaginary before the integration, and the only real number that goes imaginary to real is
An
zero.
excellent argument. What's wrong there?
That the wave function also vary. You can take a minus.
The answer to it is if the wave function is real, you don't have to do any further steps. You know that the average momentum is zero. Now we will discuss it in a couple of lectures, but I'll give you a statement. Any bound wave function, any wave function of a particle that stays around a point is real. How can I know it? Because if it had an average momentum, it won't stay around a point, right? So any particle in a box, wave function of an electron around an atom, all of these are real. Why? Because they stay there. Why do they stay there? Because their average momentum is zero. If it's not, I'll give you an example.
Oscillator.
No,
No, oscillator
Oscillator
space.
is also.
It's in a certain yes. Into the
Let me ask what happens for such. Such a wave function, and here you should pellet me with rocks because
There is no time.
no.
You can take it like this, but
Because the momentum is not zero.
That's okay.
okay.
Okay, let me put it in and do the calculation, and for simplicity, I'm in a one-dimensional world. Okay, P of x I wrote psi conjecture. Plus, okay. Okay. The only dependence on x is here. Derivative puts down ikx.
And then the out is ACD. So it's okay.
This is just a number, complex number, but number. This times this is 1. Here you have a problem with normalization because it's over. This is not normalized. Pay attention, and that's the point. But in a moment I'll explain why I write it this way, but if I ignore the normalization, I have here h bar k.
It's minus.
No,
It's out.
Somewhere
Minus I minus
It's plus.
it's plus here.
Ah, sorry.
But why one of the exponents is okay,
Con-
step back.
That's
Okay.
why it's written
Okay.
this way, exactly.
I-
Now, you can't stop me. Bullshit, this diverges. We didn't normalize the wave function. Why didn't we normalize the wave function? Because I wanted a wave function of a particle that's in a specific momentum. If you think about it, a particle that is in a specific momentum exists everywhere. I can't normalize it.
It's a delta function in the momentum, right?
It's a delta function in the momentum, meaning that in real space it's
Because the Fourier.
Fourier transform everywhere. Now, so such a situation is not physical. Right. But I didn't want at this point to introduce a wave packet and start to complicate things. But if we ignore normalization, that's the result here. And basically, now you know to calculate averages, and you know to calculate any higher moments. And we'll see in the next lecture, you can calculate variance or get the whole distribution. All of it exists. Once you know the moments, you know everything about the system. Still has nothing to do with eigenvalues and eigenfunctions. They are very important, but not yet introduced. Okay, I think we'll, for the first lecture, know what we'll do a bit more, just nice things that people are leaving, but on the other hand, we still have some time, so I'm debating with myself. Yeah, let's push on with it. an hour. Okay, so from this we can already pull out results that we are familiar with in classical mechanics. Remember, here at the moment we don't see any connection with classical mechanics, right? Doesn't look connected at all. We had a new formalism with new quantities, with new ways to calculate stuff. Does it have anything to do with classical mechanics? And the answer is, on the simplest level, yes, we can show that average quantities behave as if in classical physics. But pay attention, an average quantity is not necessarily what I measure. Newton's law. P should equal to mv. Okay. We have no operator for v in our dictionary. I'm writing it down in one dimension. It's no problem at all to expand it to other dimensions, 2 or 3. Okay? So v is dx to dt, right? Okay. Let's see if in quantum mechanics the average of P is equal to the derivative of the average of X. Okay. That's how we defined the average of X. X doesn't depend on t, so I can put it inside.
סבבה, נו, אז כן.
Okay, what did I do here? I pulled the divergence before x and subtracted the second part. Because if I write as this, I have a derivative of x times the derivative of g. So I go back to here.
I don't understand so much. How did you do this?
Which step?
The list from here to the next.
Okay.
Okay.
So here I have x outside.
Right.
Let's assume that it's inside. Okay?
It's like the derivative of two functions.
Right, so what do I have? I have either x times derivative of this, or derivative of x, which is 1 times j. That's all. Why did I do this exercise? To state the statement.
There is a reason to change now dx to dx vector.
Just to use Gauss. Well, the truth is if I'm working in 3 dimensions, even if I'm calculating x as I showed before, I have to take into account that I'm also integrating over y and z.
It's 0 because J is complex.
No, because j at infinity
Zero.
Okay.
is 0.
Okay.
I'm going back to Gauss, our
Okay.
friend, this lecture. Okay, so after all this exercise, what do I end up with? This is equal to these are just by definitions and treating the wave function square as a probability. No other ingredient. Now I want to write down the current.
You can change the gradient to d to dx because we only talk about dx.
No, I'm writing down the definition of j that we did.
But jx is only with I think.
Okay, so here
So
did I forget here?
Kavod.
No, I have it here.
The mask, right?
And now I have to multiply it.
It's supposed to say D something dx.
Actually, here I forgot the mass. Right. If you look, one is the complex conjugate of the other. Yeah.
What is the? There's just a derivative in the middle. Isn't there supposed to be a derivative of J of some whatever about
No.
function?
I'm looking only on this term. That's J.
Oh, that's the element of
Yeah, this element is 0, as we said. I
yeah.
erased it. So that's the only element that I'm left with.
Right.
Okay. So dou x,
But what about the J?
that's J.
Oh, it's just a derivative J.
We did, half an hour ago we defined J. Remember in the equation where we connected the, I'm pulling it out.
There is a two there too in the mess.
Yeah, it's written but not clear. Okay, since one is the complex of the other, and that's the definition of average P.
In the declaration of J, we have the mass already.
That's why I write it down here.
So it need to be squared.
No, mass wasn't squared.
Okay.
So this guy is average P. Over N, what we set out to show.
There's an AC minus on the left, right? In the second term.
In the second term here should be.
And where the two go to? Goes to?
One is the complex of the other, so I connect them.
And because of the I, they cancel.
They don't cancel, they add. I'm left with an I. Again, the intricacies of complex numbers. Very important in quantum mechanics. An endless source of mistakes. And very general, didn't tell you what's psi, didn't discuss at all what is the system. Just defined averages and showed that two classical quantities that we know are connected give you this connection for the average quantities in quantum mechanics. Does it mean that if I measure x, I measure p over n? No. There is a connection of averages, not for a single experiment. Okay, we'll stop here.